Okay, so this is the lecture for April 4, and what I decided to do was to go through and solve some of the problems from chapter 18, which is on electrical properties, that I felt were representative of the material covered in the chapter. And these are problems that you can certainly imagine some variation of this showing up on the quiz that we're having Wednesday, which is April 6. So first, we've got this problem 18.3 from your textbook, which says you have a plain carbon steel wire that is 3 millimeters in diameter, and you want your total system to have a resistance which is no greater than 20 ohm, and you're supposed to use the data in table 18.1 to compute the maximum wire length. So the way we're going to do this is we're going to use the expression that rho is equal to the resistivity is equal to the resistance times the area divided by length. So this gives us the geometric expression for resistivity in terms of the resistance. And we're take this and we're going to have to solve for L. And if you open your table, in the book they don't give you the resistivity, but instead they give you the conductivity. So this is going to be 1 over sigma. So we got this expression, and we have the area here, which is pi d over 2 squared for the area. For the resistance, we're going to use 20 ohm. Conductivity is 0.6 times 10 to the 7 ohm meter to the minus 1, and that is for plain carbon steel in table 18.1. And we want to find L, which means L is equal to R sigma pi d over 2 squared. So it's known, 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 and known, which means L is equal to 848 meters. And the next problem is problem 10 or 18.10, and this one asks you to calculate the drift velocity of electrons in silicon at room temperature when the magnitude of the applied external electric field is 500 volt per meter. So this problem is dealing with intrinsic semiconductors, so we're not talking about doping. And we have that the drift velocity is equal to the mobility, and we're doing the mobility of electrons, times the applied electric field. In this case, the electric field we have is 500 volt per meter, and the mobility we can take from a table in your textbook as table 18.3, and that is 0.145 meters squared volt second. And when you do that, you get a drift velocity of 72.5 meters per second. And then part B of the problem, let's change colors here, so don't get this thing mixed up. Part B of the problem says, given these circumstances, namely given the drift velocity, how long does it take for an electron to travel 1 inch, or 25 millimeters? Well, velocity has units of meter per second, and length per time is meter per second, which means we can use this relation, and we know the length. We want to find the time. The time is equal to the length, which is 25 millimeters, divided by the drift velocity, which is 72.5 meter per second. And that gives us 3.45 times 10 to the minus 4 seconds. Okay, the next problem I picked was 18.11, and this is also intrinsic semiconductor problems. And in this problem, we're told, we're given the electrical conductivity of aluminum, and we're given the electron mobility of aluminum, and we're supposed to compute the number of free electrons per cubic meter of aluminum at room temperature. So using sigma equals n e u sub e, we're interested in the number of electrons, and we want electrons per cubic meter. So in this case, we have that. We have the conductivity, and we have the mobility, and we know the charge in electrons. So we're trying to find this. We're trying to find n. So n is equal to sigma over e mu e, and when we substitute the numbers in, we get 1.98 times 10 to the 29 meters, inverse meters cubed. So these are electron per cubic meter, and I'm specifying that because part 2 of the problem, or part B of the problem, is to determine the number of free electrons per aluminum atom given the density. Okay, so we want the number of free electron atoms, free electrons per aluminum atom, and we have the density, so we know we have something which is going to be gram per cubic centimeter, which means that we're going to have to do something to get this into an expression that we can use our electron per cubic meter in. And the way we're going to do that is we're going to take this and we're going to divide it by the grams of aluminum per mole, right? So that's the atomic mass. And then to get rid of the moles, we have to have something which gives us atom per mole. And in doing this, we're going to wind up with grams canceling, atoms stay, sorry, moles canceling, and that's going to give us atoms per centimeter cubed. And then we can use this, well, times 100 centimeters cubed per 1 meter cubed to get atom per cubic meter. Combine that with electron per cubic meter to get electron per atom. So let's write out this expression in a more appropriate fashion. This is Avogadro's number times the density, which we were given, divided by the atomic mass of, what we're looking at aluminum. And we're going to get this in units of atoms per cubic meter. And that means multiply, substituting in Avogadro's number, which is known. This is a gram per mole, the atomic mass, and this is in gram per cubic centimeter. So we're going to take this and then multiply it by 100 cubed centimeter cubed per meter cubed. And that gives us atoms per cubic meter. And then we want electrons per atom. Then we want to take this expression which is cubed, and divide it all by n here, which is electron per cubic meter. These cancel out, giving us electron per atom. So we've got n, we've got rho from above, we've got Avogadro's number, atomic mass, we got the conversion of cubic centimeters into cubic meters, and when we substitute all those numbers in, we get 3.28 electron per atom for aluminum. So I mentioned several times in this class that unit analysis is really key, and that really is the case. As an engineer, you're going to find a lot of times you just don't have an equation readily available, and you have little bits of data. For example, here we started out with the density, and that gave us kind of a clue of where to start, but then we had to fill in other values, either coming from constants or tables or figures or whatever we had available to us in order to figure out how to solve the problem. So it's a good time to go through and practice unit analysis so that you can solve any of the problems that come in your future as an engineer. Okay, here's another problem I picked. This is problem 18.12, and this is dealing with excuse me. This is dealing with the intrinsic semiconductors again. And this time we're asking to calculate the number of free electrons per cubic meter of silver, assuming that there are 1.3 electrons per silver atom. And to solve this, we're given the electrical conductivity here of silver, and we're given the density of silver. So because we have free electrons per silver atom, the kind of trick here is we want to figure out the number of silver atoms per cubic meter, and then we can multiply that by 1.3. So let's figure out the number of silver atoms per cubic meter. So given grams per cubic centimeter, if we multiply that by Avogadro's number to get us atom per mole, that gives us a good start, because now we have atoms. And then we have to get rid of the moles, and we have to get rid of the mass. So if we have gram per mole, so this is the atomic mass of silver, we're going to get moles to cancel, we're going to get grams to cancel, and we're left with atoms per cubic centimeter. And we want this in cubic meter, so we're going to have to say 100 centimeters cubed per 1 meter cubed. And that we'll get rid of the cubic meters, we'll get rid of the cubic centimeters, and instead we'll wind up with cubic meters. So this is written in a little more formal fashion. This is rho Na over A Ag times 100 cubed. And that's going to give us atoms per cubic meter. And then we know that there are 1.3 electron per atom. So we multiply by 1.3. And this is going to give us, substituting in these numbers, is going to give us 7.62 times 10 to the 28 electron per cubic meter. Okay, and that's the first part of the problem, A. The second part is compute the electron mobility. Okay, let's change colors. Electron mobility. We have the conductivity, and we didn't use it up here, so that's a pretty big hint that we're going to use the conductivity for the second part. And we know that the conductivity sigma is equal to N E mu. If sigma is given, N is also given, and the charge is known. So we're just solving for the mobility in this fashion. So we have mu E is equal to sigma over N E. So this comes from the problem statement. N comes from part A of the problem. and E is 1.6 times 10 to the minus 19 Coulomb, giving us mu sub E is equal to 5.57 times 10 to the minus 3 meters squared per volt second. And there you have it. Problem 18.12. So moving from moving from intrinsic semiconductors to extrinsic, we're going to look at problem 18.25. 18.25 says that we have an n-type semiconductor of some sort, and we know the number of electrons or the number of dopant species, and we know that we're at a temperature sufficiently high that all of the dopant atoms are activated. That's going to be N, and we're given the electron drift velocity, and we're given an applied electric field. So what is the conductivity of the material? Well, we have sigma is equal to N E mu. In this case, N is given, E is known, we have to find the mobility, and we know that the mobility is related to the drift velocity, because the drift velocity is proportional to the applied electric field, and the constant of proportionality is the drift velocity. So that's given here is 1000 volt per centimeter. This is given here. We want to find the mobility, put it in. So we get sigma is equal to N E Vd over field. So now these are known, 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 known. And we can find sigma to be 0.028, right, just reading my notes, ohm meter to the minus 1. So that's how you solve problem 18.25. Here's a problem. This is problem 18.33, and in this problem statement, the textbook gives you an expression for conductivity as a function of temperature and band gap, and this is for an intrinsic material, and this is a handy equation. So we're going to be using it, and you should probably recognize it when you see it on an equation sheet in your either near or distant future. And in this expression, C is a constant, Eg is the gap, and T is the temperature. So the problem is calculate the intrinsic electrical conductivity of germanium at 175 degrees Celsius. Okay, so in order to do that, we need to get some expression for that constant C. And we can do that because in table 18.3, you have the room temperature. So when T is equal to 298 Kelvin, we have the conductivity of germanium as 2.2 inverse ohm meter. So we can take this expression now, and taking the natural log of both sides, we get natural log of sigma is equal to the natural log of C minus 3/2 natural log of temperature minus Eg over 2kT. And rearranging this, we get ln C is equal to ln sigma plus 3/2 ln T plus Eg over 2 kT. So we know sigma, we know T, K is just the Boltzmann constant. Again, we know T. Eg is the band gap of germanium, and that's also well known and is given in your textbook, table 18.3, 0.67 electron volt. And that means that now we can find natural log of C is equal to 22.38, or C is equal to 5242. Okay, and this goes back up into the expression for C, and that allows us to immediately calculate the intrinsic electrical conductivity for germanium using sigma is equal to Ct to the negative 3/2 exp negative Eg over 2 kT. So this is known, known, known. So we can just substitute and find that sigma is equal to 94.4 inverse ohm meter. And that's problem 18.33. And I want to skip this problem. Some of the problems in your textbook I'm not particularly fond of because they involve looking up constants from a table, and if you're looking up the constants for example, looking up the mobility, you might as well just actually look up the final answer. I don't really see it as something that's particularly challenging. In the case of others, though, I think that there are some equations and engineering skills that are required, and this is a problem where you're going to be combining equations to get a solution. This is problem 18.48, and basically we are asking to compute the mobility of sodium ions at a given temperature. And these are sodium ions in sodium chloride. Well, this comes from this relationship, A plus is equal to N Na plus E D Na plus over kT. So the mobility is related to the, this is the charge on the ions, because the charge per electron and the number of positive charges on the ion. This is the diffusion coefficient for sodium ions, and this is Boltzmann constant and temperature. So in this case, sodium ionizes to a +1 state. This is, again, the Coulomb per electron charge. Boltzmann constant and temperature, those are known, or they're given. In this case, they're given by the problem statement. The diffusion coefficient is not known immediately, but we remember from our chapter on diffusion in the first section of this course that the diffusion coefficient obeys an Arrhenius relationship. D0 exp negative QD over KT, right? And remember, Arrhenius relationships, those are used anytime you have some energy barrier that has to be overcome. And in the case of diffusion, for an ion to be hopping through a lattice, each time that it hops, it has to go through some saddle point, and it hops over this energy barrier to move forward. So that's why diffusion is governed by an Arrhenius-like expression. And the problem statement gives us the activation energy, QD, and it gives us the pre-exponential, which is our D0, which now means we know that, we know this, this, and this. Substituting these values in, we get D diffusion coefficient of sodium ions equal to 1.76 times 10 to the minus 14 meters squared per second. And that was the last part we needed to get the mobility. And this allows us to calculate the mobility of sodium ions to be 2.34 times 10 to the minus 13 meters squared per volt second. Okay, so that's solving problem 18.48. And now we're going to continue with dielectric type problems. And in this case, we're going to talk about parallel plate capacitors, and we are given the geometry, so that's the area, and we're given the separation, that's our L, and we're given the dielectric constant, and remember that's the relative permittivity, so that is epsilon sub r. And the question we're supposed to answer is, what is capacitance? Well, capacitance is equal to the permittivity times our geometry, so that's A divided by L. And we don't know the permittivity, but we know the dielectric constant. And the dielectric constant is epsilon divided by the permittivity of vacuum, which means that we can now write the capacitance is equal to the dielectric constant times the permittivity of vacuum, A divided by L. And substituting in all of these known values, we get a capacitance of 10 to the negative 10 farad. Now, part 2 of the problem asks us to compute the field that has to be applied across the plates in order to store 2 times 10 to the minus 8th coulomb of charge on each plate. And this comes down to us going back and remembering our relationship between voltage and capacitance, right? I mean, I should say instead, capacitance is Q over V, which we can rearrange to give us the voltage. And we also have that voltage is electric field times separation, which means that our electric field is volt per length. So, given this, we can get the electric field is Q divided by C divided by L. So now, C, we have Q is 2 times 10 to the minus 8 coulomb, given by the problem statement. L is 1 millimeter, also given by the problem statement, which means that when we substitute those values, we can calculate an electric field that must be 2 times 10 to the 5 volt per meter. And this is problem 18.51. And last but not least, we will look at problem 18.55, which is similar to the previous problem in that it's dealing with a parallel plate capacitor. In this case, we're saying that 2 times 10 to the minus 10 coulomb must be stored on each plate, and we're given the area and we're given the separation, Q. And the problem, first part of the problem is what voltage must be applied given the dielectric constant is 3.5. So we have some material between the plates. So we have C is equal to Q divided by V. And we also know that C is related to the permittivity of the material. Epsilon A over L. And we don't have that, but we have the dielectric constant, which is epsilon sub r. And we know that epsilon sub r is equal to epsilon divided by epsilon 0, which means that we can substitute in for epsilon r, epsilon 0, A over L. So now we have this left side is equal to the right side, and the dielectric constant is known, the permittivity of vacuum is known, the area and the length are given, the charge that we want to store is given, and we want to find the voltage. The voltage is equal to QL over epsilon sub R epsilon sub naught A. These are all known, and this gives us 39.7 volts. Okay, so that's part A. Part B asks us to redo the calculation, but now what would happen if instead of having a dielectric medium between the plates, we have just vacuum? Well, what that means is that for part B, we're getting rid of the relative permittivity, and we're just having the permittivity of vacuum, which is great. Which means that now part B, V is equal to 139 volts. And there's a fairly significant difference here. Okay, part C says, what are the capacitance for part A and B? So we want to be able to use these voltages to get the capacitance. And this is just using C is equal to Q divided by V. Q is given in the problem statement. V is solved in part A and part B. And that means that I'm going to call this C sub part A. C sub part A is equal to 5.04 times 10 to the minus 12 farad, and C sub part B is equal to 1.44 times 10 to the minus 12 farad. So it's more common for us to refer to that as a picofarad, right? So this is 1.44 picofarad. Remember, when you're dealing with units, times 10 to the minus 3 is milli, like millimeter. 10 to the minus 6 is micron, with a little Greek m, or micron, for micrometers. That's how I think of it. Times 10 to the minus 9 is nano, and I think of that as nanometers. And then 10 to the minus 12 is pico. So these are 1.44 picofarad, and that is 5.04 picofarad. Part D says compute the dielectric displacement for part A. So the dielectric displacement, that is coming from this expression, D is equal to the permittivity of vacuum times the field plus the polarization. And the polarization is epsilon naught, epsilon r minus 1 field, which we can substitute in to get D is equal to epsilon naught field plus epsilon naught epsilon r1 E, which simplifies to epsilon naught epsilon r times field. And we got the field, but we don't know what the field is. However, we know what the voltage is. And we know what the separation is. And we know that the electric field can be written in terms of the voltage and the separation. So this is equal to, voltage divided by length. And if we do that, a piece of paper, if we do that, we get, and these are known. This is going to give us D is equal to 3.07 times 10 to the minus 7 Coulomb per square meter. So that gives us the displacement. And part E says compute the polarization. And we'll do that here. So given this expression for the polarization, we know permittivity of vacuum, the relative permittivity or the dielectric constant. That means we can say P is equal to epsilon naught epsilon r minus 1, and then in place of electric field we're going to use the voltage and the length, V over L. So now we have this is known, and known, and when we substitute in, we get a polarization equal to 2.2 times 10 to the minus 7 Coulomb per meter squared. And this is how you solve problem 18.55. And that's a set of problems that I think are good examples of what we see in chapter 18, and problems that I think that you should be able to solve coming out of this class. So please do practice these, and remember you have a quiz on Wednesday when I get back covering this chapter, and then Friday this week I will be out again, so on Friday we will have another video lecture. Thank you very much, and I will see you on Wednesday.